James Clerk Maxwell, the architect of modern physics. In the pantheon of scientific giants, few names shine as brightly as James Clerk Maxwell. Yet his contributions remain surprisingly unknown to the general public. While Einstein and Newton are household names, Maxwell, whom Einstein himself credited as his inspiration, transformed our understanding of reality in ways that continue to shape our daily lives. From the smartphone in your pocket to the microwave in your kitchen, from radio waves carrying your favorite music to the light illuminating this page, all trace their theoretical foundations to the elegant equations of a 19th century Scottish physicist. Born on June 13, 1831, in Edinburgh, Scotland, James Clerk Maxwell entered a world on the cusp of industrial revolution. His father, John Clerk Maxwell, was a lawyer with a passion for science and technology, while his mother, Frances came from a family of considerable intellect. Young James grew up at Glenlair, the family estate in Galloway, where his curiosity about the natural world flourished. He was the sort of child who would ask what's the go of it about everything he encountered, a question that would define his scientific career. Tragedy struck early when Maxwell's mother died of abdominal cancer when he was only 8 years old. This loss profoundly affected the sensitive boy, but his father ensured he received an excellent education. After an unsuccessful stint with a private tutor, Maxwell was sent to the Edinburgh Academy at age 10. Though he was initially mocked for his rural accent and unusual clothing, he soon distinguished himself through his mathematical brilliance, publishing his first scientific paper at the remarkable age of 14 on mechanical methods for drawing mathematical curves.
Maxwell's academic journey took him to the University of Edinburgh and then to Cambridge University, where he studied at Trinity College, and later became a fellow at the same institution. It was during these formative years that Maxwell began to display the unique combination of mathematical sophistication and physical intuition that would characterize his greatest work. Unlike many mathematicians who dealt purely in abstractions, Maxwell possessed an uncanny ability to visualize physical phenomena and translate them into elegant mathematical language. His early work on color vision and optics demonstrated this gift. Maxwell proved that any color could be created by mixing red, green, and blue light in appropriate proportions, the principle behind modern television and computer screens. In 1861, he produced the world's first color photograph, a tartan ribbon, by combining 3 black and white photographs taken through red, green, and blue filters. This achievement alone would have secured his place in scientific history, but it was merely a prelude to his revolutionary work on electromagnetism. The story of Maxwell's equations begins with the experimental work of Michael Faraday, a self-taught English scientist who discovered the fundamental relationships between electricity and magnetism through careful experimentation. Faraday had introduced the concept of lines of force to explain how electric and magnetic influences propagate through space, but he lacked the mathematical training to express these ideas rigorously. Maxwell, recognizing the profound importance of Faraday's insights, set himself the task of translating them into mathematical form. Between 1861 and 1862, Maxwell published a series of papers that would culminate in his masterwork, a dynamical theory of the electromagnetic field, presented in 1864. In this revolutionary paper, Maxwell proposed that light itself was an electromagnetic wave, a self-propagating disturbance in the electromagnetic field that travels through space at a finite speed. He calculated this speed from electrical measurements, and found it matched the known speed of light with remarkable precision. This was no coincidence, Maxwell realized. It was proof that light, electricity, and magnetism were all manifestations of the same fundamental phenomenon. Maxwell's equations, as they came to be known, consist of 4 elegant mathematical statements that describe how electric and magnetic fields are generated, and how they interact with each other and with matter. These equations predicted the existence of electromagnetic waves of all frequencies, not just visible light. They implied the existence of radio waves, which Heinrich Hertz would experimentally confirm in 1887, nearly a decade after Maxwell's death. They also predicted X-rays, gamma rays, infrared radiation, and ultraviolet light, the entire electromagnetic spectrum that modern technology exploits. The philosophical implications of Maxwell's work were equally profound. His equations suggested that electromagnetic waves could propagate through empty space, without any medium, challenging the prevailing belief in the luminiferous ether, a hypothetical substance thought to fill all of space. This conceptual revolution paved the way for Einstein's theory of special relativity, which emerged directly from careful consideration of Maxwell's equations and their implications for the nature of space and time. Maxwell's scientific contributions extended far beyond electromagnetism. In thermodynamics and statistical mechanics, he made equally groundbreaking contributions. He developed the Maxwell-Boltzmann distribution, which describes the statistical behavior of gas molecules, introducing probabilistic thinking into physics at a fundamental level. His Maxwell's demon thought experiment, proposed in 1867, raised profound questions about the relationship between entropy, information, and the second law of thermodynamics, questions that remain relevant to quantum information theory and the foundations of statistical mechanics today. Despite his towering intellect, Maxwell remained remarkably humble and possessed a dry sense of humor. He was deeply religious, seeing no conflict between his scientific work and his Christian faith. He served as the first Cavendish Professor of Physics at Cambridge University, where he oversaw the construction of the Cavendish Laboratory, which would become one of the world's premier physics research institutions. Under his direction and that of his successors, the Cavendish would produce dozens of Nobel laureates and countless fundamental discoveries. Maxwell's personal life was marked by his devoted marriage to Catherine Mary Dewar, the daughter of the principal of Marischal College in Aberdeen. Though they had no children, their partnership was one of deep intellectual and emotional companionship. Catherine assisted him in his experimental work, particularly his color vision research, and provided him with the stability and support that enabled his scientific achievements. Tragically, Maxwell's life was cut short by abdominal cancer, the same disease that had claimed his mother. He died on November 5, 1879, at the age of only 48. The world lost him just as the full implications of his work were beginning to be understood. Maxwell faced his death with characteristic courage and faith, working on his scientific papers almost until the end. The legacy of James Clerk Maxwell is difficult to overstate. His equations unified electricity, magnetism, and optics into a single coherent framework, completing the classical theory of electromagnetism that remains valid today for all non-quantum phenomena. Every wireless technology, from radio and television to Wi-Fi and cellular communications, relies on the electromagnetic waves he predicted. The development of radar during World War II, the invention of the laser, the creation of modern telecommunications infrastructure, all rest on the foundations Maxwell laid. Perhaps more importantly, Maxwell's work provided the template for modern theoretical physics. His field theory approach, treating electricity and magnetism as properties of space itself rather than as direct interactions between distant objects, became the model for Einstein's general relativity, and for the quantum field theories that describe fundamental particles and forces, the standard model of particle physics. Our current best theory of nature's basic constituents is expressed in the mathematical language that Maxwell helped create. In the estimation of many physicists, Maxwell ranks alongside Newton and Einstein as one of the three greatest physicists who ever lived. Richard Feynman called Maxwell's discovery the most significant event of the 19th century, arguing that from the long view of history, even the American Civil War would pale in significance compared to Maxwell's equations. Albert Einstein kept a photograph of Maxwell on his study wall, alongside pictures of Newton and Faraday, the intellectual ancestors of his own revolutionary work. Today, more than 140 years after his death, James Clerk Maxwell's influence continues to grow rather than diminish. As we enter an age increasingly dependent on electromagnetic technologies, from quantum computers to photonic circuits, his insights remain as relevant as ever. The quiet Scottish physicist who asked, "What's the go of it?" discovered answers that illuminated not just how nature works, but provided humanity with tools to reshape the world.